Welcome to my session at Oracle Database World. My name is Toon Koplaars. I'm an architect within the real-world performance team. We are a part of the database development organization. And as a member of that team, I very often get engaged with both internal development application groups as well as customers when they move and start using our autonomous data warehouse or autonomous transaction processing offerings. And in that role, I'm going to present today showing you how working with a large number of rows in autonomous data warehouse should be done in a good manner. So here's a quick overview of what I will be talking about today. I'm going to start with a core performance principle and show you why that is a core performance principle when you deal with large number of rows in ADW. Then in the remainder of the session, I'll be applying that principle when you want to either get rows inside ADW or process rows that are already inside Autonomous Data Warehouse, or when you want to unload, when you want to get rows out of ADW. So here we go. Allow me to introduce an analogy to show you the core performance principle. So in logistics, when you want to move a large number of items between two physical warehouses, you usually do it with bulk processing, right? You're not going to use a regular vehicle to drive back and forth, shipping only a few items every time when your intention is to move a lot of items from the left to the right. Instead, you're going to use bulk processing. You're going to rent a truck, preferably load all the items that need to be shipped, and then just drive once from the left to the right and then unload the items. So the benefits are pretty obvious in this analogy. You get more work done with less cost and effort, and probably in less time as well. Now, when you use a regular vehicle, you're basically switching context a lot of times. You switch context on the left once you've loaded the items and start driving to the right. And then you switch context on the right again when you've arrived at the destination and start unloading the items. And you switch context again, driving empty back to get the next set of rows. Now, these context switches constitute overhead in dealing with this moving of all the items. Now, in software systems, we have, this is true for software systems as well, but instead of items, we ship and process a huge number of rows, typically in a data warehouse application. And we move these rows between processes, between operating system processes. And these processes can be on different servers, for instance, the Java application server versus the database server, a dedicated foreground process on the database server. They can be processes running on the same server. If you data pump, import a lot of rows into the database on the same database server, or they can even be within a same process, within different major modules. So in Oracle, that would typically moving the rows between the PL/SQL and the SQL engines. Now, we have super fast CPUs nowadays. And the question is, should I even care about these context switches between processes or between major modules within a single process? Well, let's look at the numbers, because I think you should care, especially when we start dealing with a large number of rows. Because the principle is all about you really want to minimize the context switches between the processes or components. Because getting into an operating system process or getting out of an operating process, you always have an additional CPU cost. And this can only be a few tens of microseconds. So you think that's negligible. Now, if you move rows between processes on different servers, there will be the network involved. So you have an inevitable latency cost per hop, and this can easily be a few hundreds of microseconds. And the three strategies that you can use when processing many rows in data warehouse applications are row by row, traditional row by row processing, bulk processing, which is basically array by array processing. You process a bunch of rows each time. And finally, you have the set-based processing approach. This is where you write a single SQL statement to deal with your requirement in one go. And as we go down in these three strategies, the number of context switches obviously decreases. Yeah, so it's sort of like analogy analogous to using a regular vehicle versus a truck or versus a big ship to deal with these requirements. Now, these microseconds, they really become real overhead if you start processing millions of rows. Let's suppose we need to process 100 million rows and assume that we have a total cost in terms of CPU and latency of 220 microseconds. Let's say a couple of hundreds on the network, a couple of tens in the CPU. So 220 microseconds per row. If you do the multiplication, that's already 6.1 hours of overhead. If you start employing array processing, let's say process not row by row, but 100 rows at a time, and then 100 rows the next time, etc., then you're still looking at 3.7 minutes overhead to get your processing done in an ADW application use case. Whereas if you have set-based processing, the overhead will become 0. Yeah? So these are just overheads. And the core performance principle is if you minimize these context switches, you minimize the overhead. And this, again, overhead will be considerable present if you deal with millions of rows. So let's apply this core performance principle when you want to get rows in ADW. Well, getting your rows in ADW can be done in a few ways. You can either write your own module, where you write a Java program on an application server which reads flat files that are also loaded on file systems on your application server, and you then generate insert statements towards the autonomous database. And again, here you can do row-by-row processing or array-based processing. But both will still be heavy CPU and network latency, will still have heavy CPU and network latency overheads because of the context switching going on between the application server and the database server. If you use set-based processing, you obviously would have to place your file with the rows that need to be loaded first into a bucket on the object store, which sits much closer to your autonomous data warehouse. And then you can create an external table on top of that file or set of files. Once you've created the external table, which I call here a do-it-yourself external table approach, you can then write a single set-based insert into some staging table, select star from that external table. An even better way to do that is to use the copy data procedure that we supply in the DBMS Cloud package. That procedure basically does the same under the hood. It also creates an external table, but you don't have to create it yourself. It also uses a direct load very similar to the insert statement you see here on this slide, and thus employs set-based processing. There's a small advantage here as well, is that we provide a data dictionary view, DBA load operations, where you can monitor the progress of the load as it is executing. Now, one thing to keep in mind is make sure that the bucket of your object store sits in the same region as your ADW database. The reason being obvious. If that's not the case, you will have your network cost and overhead again. A couple of other things that I want to mention when you want to get a large number of rows inside ADW. You may want to consider using the medium or the high service to get parallelism. Since you use a set-based approach, using the medium and the high service enables the database to parallelize the insert statement. So we'll have multiple processes reading at the same time from the file or files and inserting at the same time into the target staging table. You can even consider reconfiguring the medium service to get an even higher degree of parallelism than the default. I'll explain that in a few minutes. The other thing, and this is less known, you may want to consider for staging tables. This is a relatively new feature in Autonomous Data Warehouse, where you can create a table and you just add the for staging keywords here on the slide. What that makes the table is, it makes the table not being compressed, and it also makes the table such that when you do a direct load, you don't have the overhead of statistics computation. Instead, the optimizer will use dynamic sampling once you start using the staging table. The other property of a for staging table is that when you drop the table, it won't go into the recycle bin. By default, it will be gone. So with for staging tables, you run a little bit insert speed because no compression or no statistics on load is going on. Now, moving on to processing rows inside ADW. Well, the message here is actually really simple. It is easy to get good results as long as you don't ship rows out and decide to process them on the application server and then ship them back into the database. Instead, employ set-based SQL, set-based queries with joins and subqueries and group bys and havings and what have you to state what you want the query to be doing, and let the optimizer parallelize this requirement in the medium and in the high services. Now, there are a few things that I want to give you that you should pay attention to. And that is, you want to help the optimizer to be able to come up with a good execution plan. So there's 4 things that you need to be aware of. So number 1, on the tables that your query is accessing, make sure you have not null constraints on the columns that always have a value. Also, declare primary keys on dimension table join keys and foreign keys on fact table join keys. They need not necessarily be enforced. You can define them as rely no validate, such that they don't give you an overhead when loading data, but they will still help the optimizer come up with good execution plans. Second, have correct data types. So in terms of the join keys, it's really important that the join columns on both sides have the exact same data type, as well as in size, the maximum length, and if there are numbers, as well as in the precision. So you want to use date for dates. You don't want to over-dimension varchar2 columns. For instance, declare every varchar2 column with its maximum length 4000. And you want to definitely avoid data type conversions like toNumber, toDate, or toGar in your SQL where clause queries. Thirdly, do consider partitioning your fact tables. In the real world, very often, more often than not, this will be on the time dimension, because the majority of your queries will very likely always have a predicate on the time dimension. This allows the optimizer to come up with good partition pruning strategies, making it scan less rows than are available in the whole table. Finally, of course, an obvious point, you need up-to-date statistics. Now, luckily, in the autonomous database, the word autonomous does it. This is already taken care of by autonomous database. So every 15 minutes, we make sure that still statistics get refreshed and all statistics are usually up to date. So with having these things in place, you gain the optimizer being able to come up with better cardinality estimates. That automatically results into better execution plans, more access paths become available, and you give the ability to the optimizer to perform many transformations and optimizations. And the partition pruning can happen, as I mentioned on the prior slide. Yeah, so it's easy to get good results as long as your database design is sound and your queries don't have these implicit data type conversions going on. So the optimizer can generate very efficient parallel plans that exploit then all Exadata magic that's available, because Exadata is the platform on which our ADW databases are hosted. Now, I mentioned earlier that you may want to consider reconfiguring the medium service. On ADW, we provide 3 services to which you can connect when you log into an autonomous data warehouse. And the service basically drives what the degree of parallelism will be of the statements that you execute within your session. So only in medium and high, we get a degree of parallelism higher than 1. So I have a screenshot here of a small data warehouse PDB pluggable database where my CPU count is 4. Then by default, I get a DOP of 4, both in the medium and in the high service. But there's a second property here, the left column, which is called concurrency limit. The concurrency limit denotes how many statements can run at the same time concurrently. And you may want to decrease the medium 5 there, because if you decrease the concurrency in medium, you can actually get a higher degree of parallelism than you have in the high service. Yeah, so maybe 3 statements at the same time is good enough for you in your 4.0 CPU PDB. Then queries will actually run probably faster in the medium service than they would have in the high service, because you can't touch the DOP of 4 in the high service. Now, you can also do this programmatically. We have a CS Resource Manager package in the database. With the update plan directive, you can modify, adjust the concurrency limit, and you can view the current settings via the list current rules, which basically gives you the same thing that you see in the screenshots here. Another thing to be aware of, once you use set-based processing and chose to have your SQL be parallelized, then do be aware that we provide active SQL monitor cases for the executions of those statements. So in case you think your statement should run faster, just pull the active SQL monitor report for your statement, and it will detail at a high granularity exactly how your statement was executed and where time was spent. Did we spend most time in the database tier, or did we spend most time in the storage cells doing smart scans? This is your number one report to go to when you want to do some diagnosis on performance tuning for your SQL statements. Another thing to be aware of is this CPU and storage scaling. So on your PDB, you can enable what's called CPU auto-scaling. When you enable that, then immediately your PDB will have available 3 times more CPUs. Now, the effect of that in terms of the concurrency for medium and high will be that those concurrencies will also go up by a factor of 3. So here you see the screenshots of that same PDB, and I've now enabled auto-scaling. And you see that the high concurrency limit has gone up from 3 to 9, and the medium concurrency limit has gone up from 5 to 18 in this case, so a little bit over 3x. Now, if I now bring back the 18 concurrency limit to 5, you can see that I can get really high DOPs in the medium service. Yeah, so and this can really help speed up some of your large SQL statements processing many number of rows. So this helps queries that spend most time on the database tier. And again, the SQL Monitor report will tell you if your query is spending most time on the database tier or in the storage tier. Storage autoscaling will allow more storage for your PDB, but it has a side effect that your PDB also gets a larger share of the flash cache inside the storage cells. And once you get a larger share of the flash cache, that then speeds up your I/O bandwidth. Simply translates to faster smart scans. So this helps queries that spend most time on the storage tier. Again, your SQL Monitor report will show you whether your query is spending most time in smart scans or not. One other important point of interest that I want to mention, because I see it more often than not, and this is a thing which I refer to as messed up compression health. So on ADW, when you create a table, by default, all the rows will be HCC, hybrid columnar compressed in the query high mode. So we'll get very compact compression units that has all your rows of those tables. However, when you do large updates or merges that do updates as part of the merge, the rows that get updated will actually migrate out of those highly efficient compressed compression units, and they will be moved to traditional OLTP compressed blocks, and they leave a pointer behind in the CU in the compression unit. That can have a tremendous impact on a smart scan performance, because when we start smart scanning, we detect these pointers and we then have to stop the smart scan and go out and fetch the single block that has the rows that were updated and migrated to other blocks. So instead of doing large updates or merges, consider doing a set-based delete of the rows that you want to update and then reinsert them with the updated values as they would have been after the update. Or if you still want to continue doing updates or merges, be aware that this affects the compression health of your tables, and regularly schedule alter table move or alter table partition move on lines to restore the compression health of those segments. Finally, getting rows out of ADW. Here too, you can write your own module on your application server, which spools files to a file on the file system in the application server. Or you can use our command line tools such as SQLCL or SQL+. But both need lots of development programming work to get the unload done in parallel. And of course, you have the inevitable network latency overhead between the application server and the autonomous database. What you may want to consider again is using the object store to unload to. And this can be done in two ways. Traditionally, you could do it with UTL file, but then you'd first have to write to a database directory and then move your file onwards to the object store. Again, in UTL file, you have a considerable development effort because you have to do it yourself in terms of making it parallel, making sure you introduce multiple threads and divide the data to be unloaded across those threads. It's again far better to just use a supplied export data procedure that we have in the DBMS Cloud package. It supports various output formats, data pump, which is of course Oracle proprietary, or various text formats, comma separated values, JSON, XML, and Parquet. With data pump, as soon as you specify multiple target files, it will automatically parallel unload. If you choose to use one of the text-based files, you may want to combine the DBMS Cloud export data with DBMS Parallel Execute. So DBMS Parallel Execute allows you to spawn multiple threads that start working on various export calls from the export calls from the DBMS Cloud package. A colleague of mine, Dave Allen, has written a short blog post that has a very simple and handy code example and brings you up to speed on how to do that and be able to unload data really fast using a combination of DBMS Parallel Execute and DBMS Cloud. So with that, I'm coming to an end of my presentation. I would just like to summarize the key takeaways for you today. If you want to get data in and out on a daily basis on ADW, you should use DBMS Cloud, copy data or export data. You want to maximize the use of set-based SQL when you process many rows inside the autonomous data warehouse. Please do have constraints, correct data types, and partitioning in place, because that will help the optimizer come up with efficient execution plans that can be parallelized. Choose the right service, maybe even consider medium instead of high, because you can get higher DLPs in medium than you can get in high. And auto-scaling, as both on the CPU and the storage layer, can be a cheap way to increase the DLP and thus reduce the elapsed times of your queries even more because of being able to use more DB CPU or getting more I/O bandwidth. And with that, I would like to thank you, and I hope you enjoy the rest of Oracle Database World.